There is a harbor on the coast of Italy that has been standing in salt water for 2,000 years. The concrete pillars that hold it up were poured before the fall of Rome. They have survived every storm the Mediterranean could throw at them. They are still there, still solid, getting stronger. Meanwhile, the highway you drove on this morning is already falling apart. 40 years old, maybe 50, and it is cracking, spalling, chunks of it breaking off in your hands if you pull hard enough. We are supposed to be better at this. We have supercomputers, materials science, engineers with degrees the Romans could not have dreamed of, and yet the concrete we pour today will be rubble in a human lifetime, while theirs has outlived empires. This is not a mystery of lost recipes or ancient secrets. We know exactly what the Romans put in their concrete. We have analyzed it down to the crystal structure. The mystery is why we stopped. Because what they built was not just stronger. It was designed to heal itself, to grow tougher with time, to turn the thing that destroys our concrete into the thing that makes theirs immortal. The Romans built an empire on it. We forgot how. And now, finally, we are starting to remember why that was a catastrophic mistake. In 1985, a geologist named Marie Jackson flew to Italy to study Roman harbor concrete. Not because anyone thought it was interesting, because they thought it was impossible. The concrete in Rome's harbors had been underwater for 2 millennia. Salt water is the single worst thing you can do to modern concrete. It corrodes the steel reinforcement. It dissolves the cement paste. It turns a solid structure into crumbling mush in decades. The Romans had no steel, no rebar, just concrete, sitting in the ocean, getting battered by waves. And it was not just surviving. It was pristine. Jackson took core samples from a breakwater called the Portus Cosenus, built around 100 BC. Back in the lab, she put the samples under an electron microscope and looked at the atomic structure. What she found was a mineral that should not be there. Aluminum tobermorite, a rare crystal that only forms under extreme heat and pressure, deep in the Earth's crust, or in laboratories where we cook cement at 200 degrees Celsius for months. The Romans did not have laboratories. They did not have high-temperature ovens. They mixed their concrete cold, poured it into wooden forms, and walked away. And somehow, sitting in seawater, it grew this crystal anyway. Tobermorite is not decoration. It is the reason the concrete is still standing. It is harder than the original cement paste. It locks the structure together at the molecular level. And it only forms because of what the Romans put in the mix, and what we deliberately took out. The secret is volcanic ash. The Romans did not invent concrete, but they did something no one else had thought to do. They stopped using river sand and started using the ash from volcanoes. There is a volcanic region near Naples called the Phlegrean Fields. The ash there, called pozzolana, is rich in silica and alumina, reactive minerals that the Romans found would bind with lime to form a hydraulic cement, a cement that hardens underwater. This was revolutionary. Greek concrete crumbled in water. Egyptian mortar dissolved. Roman concrete set solid, even at the bottom of a harbor, because the volcanic ash was doing chemistry that normal sand could not. Modern concrete works differently. We use Portland cement, limestone baked at 1400 degrees Celsius until it fuses into a new compound. It is strong. It is consistent. It is also inert. Once it sets, the chemistry stops. What you poured is what you get, forever. Roman concrete never stops reacting. The volcanic ash is chemically unstable. It wants to bond with anything it touches. So when seawater flows through the tiny cracks that form in any concrete, it does not corrode the structure. It delivers dissolved minerals, calcium, silicon, aluminum, and the ash uses them to grow new crystals. The concrete heals itself. The cracks fill in. The structure gets denser, stronger. A Roman breakwater is tougher at 2,000 years old than it was the day it was built. Marie Jackson found aluminum tobermorite growing directly inside the cracks, not just filling them, reinforcing them. She found another crystal, philipsite, doing the same thing. The concrete was not decaying. It was evolving. So why did we stop using volcanic ash? Because we got better at making heat. In the 1800s, engineers discovered they could bake limestone hotter and faster than the Romans ever could, and produce a cement that set hard in hours instead of weeks. Portland cement was a miracle of the industrial age. Cheap, reliable, strong enough to build skyscrapers. And it had one fatal flaw no one cared about, because no one was thinking past the next century. It could not heal. Every crack was permanent. Every freeze-thaw cycle made it worse. The concrete we built our entire modern world on was designed to crumble. Here is what that mistake costs. The United States has more than 600,000 bridges. Nearly half of them are over 50 years old. More than 40,000 are rated structurally deficient. Not old. Deficient. As in, dangerous to cross. Fixing them will cost hundreds of billions of dollars. And fixing is the wrong word, because we are not fixing them. We are replacing them, tearing them down and pouring new concrete that will last another 50 years before we have to do it again. The Romans built the Pantheon in 128 AD. Its dome is still the largest unreinforced concrete dome on Earth. It has no cracks, no steel, no repairs. It has been standing for 1,896 years, and it will still be standing when every bridge we are building today is rubble. We did not just forget how to build concrete that lasts. We built an entire civilization on concrete designed to fail. Our roads, our buildings, our water infrastructure, all of it on a clock, ticking down. And it gets worse. Making Portland cement is an environmental disaster. That 1,400-degree kiln requires burning vast amounts of coal or natural gas. The chemical reaction itself releases carbon dioxide directly from the limestone. Cement production alone accounts for about 8% of global carbon emissions. 8%. That is more than aviation. The Romans made their concrete cold. No kiln, no fuel, just volcanic ash, lime, seawater, and time. The carbon footprint was nearly zero, and it lasted 40 times longer. So why are we not using it? For decades, the answer was that we did not understand it well enough. Roman concrete takes weeks to cure. It is inconsistent. Every batch is different because every volcano is different. You cannot engineer a highway system on a material you do not fully control. But that is changing, because in the last 10 years, researchers have stopped treating Roman concrete like a relic and started treating it like a blueprint. In 2023, a team at MIT and Harvard published a study that changed everything. They were not looking at volcanic ash. They were looking at something everyone else had dismissed as a mistake. In every sample of Roman concrete, there are small white chunks of lime scattered through the mix. For decades, scholars assumed these were contaminants, lumps of poorly mixed quicklime that never dissolved, evidence of sloppy craftsmanship. The MIT team did not assume. They analyzed the lumps with advanced imaging and found they were not accidents. They were the entire point. The Romans were using quicklime straight from the kiln, hot lime, not the smooth slaked lime we use today. When you mix hot quicklime with wet aggregate, you get an extreme chemical reaction: heat, steam, and small pockets of pure lime that do not fully dissolve. Those pockets sit in the concrete like chemical batteries. When a crack forms and water seeps in, it dissolves a little bit of the lime. That released calcium reacts with carbon dioxide in the water or the air and recrystallizes as calcium carbonate, limestone. The crack fills itself in. The concrete does not just heal. It remineralizes. The lime clumps we thought were flaws are a self-repair system, embedded in the structure, waiting to activate the moment damage occurs. The team tested it. They made concrete with hot mixed quicklime, deliberately cracked it, and exposed it to water. Within 2 weeks, the cracks sealed. The healed concrete was as strong as the original. They had recreated a technology that had been lost for 1,500 years. And they did it without volcanic ash. That matters, because there are not enough volcanic deposits near every construction site on Earth. But limestone is everywhere. If we can make self-healing concrete from heat-treated lime and seawater chemistry, we can use it anywhere. Marie Jackson's team went further. They are testing Roman-inspired concrete mixes with seawater and volcanic rock in real marine environments. Early results show the same crystal growth, the same strengthening over time. One sample, submerged for 5 years, is measurably denser than when it was poured. We are not just rediscovering this. We are improving it. Modern materials science can tune the chemistry in ways the Romans never could. We can control the cure time, adjust the strength, predict the self-healing rate. The concrete we build with 50 years from now could last 500 or 5,000. We have the knowledge. The question is whether we will use it. Here is the uncomfortable truth. We knew Roman concrete was better. We have known for decades. We have studied it, published papers on it, marveled at it in museums. And we kept building with the inferior version anyway, because it was faster, cheaper, and good enough for the lifetime of whoever signed the contract. That is not engineering. That is planned obsolescence applied to infrastructure. We built a disposable civilization. The Romans did not have that luxury. They were building an empire they believed would last forever. So they used materials that would outlive them, not because they were smarter than us, because they were thinking past their own lifetimes. Some of their aqueducts still carry water. Their roads are still walked. The Pantheon still stands open to the sky, its concrete dome unreinforced, uncracked, untouched for 2,000 years. We tore down that kind of thinking the moment we decided 50 years was long enough. And now, finally, we are starting to pay for it. Crumbling bridges, dissolving seawalls, highways that need repaving every decade. But the science is there now. The chemistry is decoded. We can build concrete that heals itself, strengthens with age, lasts millennia. We can do it with lower emissions, less energy, and materials we already have. The only thing stopping us is the choice. Do we keep building for the next 50 years, knowing we are leaving our children a world of crumbling infrastructure and endless repair bills? Or do we start building like the Romans for the next 2,000? Because here is what 2,000 years of Roman concrete proves. Empires fall, languages die, entire civilizations vanish. But if you build something well enough, it will still be standing when everything else is dust. The knowledge of how to do that was never lost. We just stopped caring. Maybe it is time we did again. If you want to see what else we lost when we stopped thinking long-term, that one will rewrite everything you thought you knew about the ancient world.